The second half of today's video series, we're going to focus on file system implementation. So how exactly a file system from within the black box is implemented, how its internal mechanism works to support a unified management, a unified view for the upper level users to get access to tens of thousands of files and directories managed by a file system. So a file system internally, it uses multiple on-disk data structures that collectively work together to provide a unified view that organizes tens of thousands of different files and directories and paths together to provide ease of use of file system related APIs interfaces to the upper level applications and users. And these users applications include both user level programs, user level processes, together with the system level software. For example, operating system also uses file system for storing and managing the data persisted and durably stored on external secondary storage systems, such as secondary storage devices, such as disks or flash SSD devices. So the question to answer is, how does a file system, Unix or Linux related file system, represent files and directories and organize these on-disk data efficiently, okay? And regarding file system operations, so the question to answer is how the on-disk data structures get touched, get interacted when performing a specific file system related operation. For example, when performing a make dir to try to make a directory and tries to read a file, write a file, and so on. Okay. And we're also going to talk about the file system related data locality and data layout policies and specific optimizations that could be used to optimize the data layout so as to better optimize performance. Okay, so first let's look into the specific on-disk data structures that are used to represent the on-disk files and on-disk directories. Okay. So, but before getting down to the detail, let's first talk about motivation. So why at all we need to design a hierarchical file system with a hierarchical namespace, specifically hierarchical directory tree-based file system structures, right? So why not just strictly create a naive flat with a persistent data store with a flat namespace? Okay, so the input is just simply a big array of on-disk bytes or disk blocks. And what we want is we just simply want to support the basic read and write operations, the basic I/O functionality. Okay, so we could just straightforwardly build a flat persistent data storage, for example, a key value store, right? That just exposes simple get and put APIs. Get for read and put for write. Okay? Let's do APIs. And each file just simply associate with a unique key, and this key would be used as input of a hash function, and the result of the hash function is just a random hashed value that is used to internally index a particular file, okay? And so that you could use a flat table, for example, a hash table. To keep track of the file, okay? And how to perform in situ read and write is you can just manipulate the offsets to facilitate these non-sequential random IO operations within a particular file, within a single object. And each object is associated with a unique key, okay? Kind of like a key value store. So what good do we have if we want to design a naive, flat, namespace-based persistent key value store instead of file system? So put it differently, what desirable features does the file system provide beyond what a naive, flat, persistent data store, key value store, data storage would be able to provide, right? So there are a lot of desirable features, desirable properties, naturally enabled by and brought by file system to the end users. So the very first important feature is the human readable string-based file names, right? So that you could just you could just organize different directories by assigning them with human understandable, human user-friendly names, string names, instead of having, random, plain, digital-based key names, key IDs instead of that. Okay, so this is the first important benefit. And it does bring other benefits as well. For example, hierarchy, right? So a user naturally demand to organize data in a hierarchical manner, right? So this directory or path kind of name abstraction naturally provides this kind of benefits, hierarchy, names within names. And it's really easy to use. It's good for organizing different files and different directories under different places. And some other notable benefits include but not limited to the changeable file names, flexible file names, and soft link, hard link, and these kind of desirable features are all enabled by a file system. A Unix-like file system, even Windows-like file system, they provide all these different kind of features, okay? So these are all the benefits that cannot be enabled by a naive, flat, namespace-based, persistent key value store-based kind of system, okay? So all these features, it require a variety of on-disk data structures. So let's next take a look at what exactly on-disk data structures that are needed in order to support these features. So in terms of common file system data structures, let's first take a look at the so-called data blocks. So in this slide, it shows a really simplified toy-like example of a toy-like disk image. And assume this disk is already formatted and used to store this whole file system image. Okay? So this disk, it consists of a total number of 64 disk sectors or so-called data blocks. And starting from the 9th data block under index number 8 all the way to the end of it, which is under index 64. Okay, so this range, a total number of 56 disk blocks. This is so-called the data region, which are preserved or reserved for storing the data blocks, for storing files and directories. Okay. So the next set of data structure is the inode table, is the inode indexing data structure. The inode data structures. So as you may already note here, the first 8 disk sectors are reserved for storing metadata information. So out of the first 8 directories, out of the first 8 blocks, the last 5 out of it are reserved to store the inode data structures. Okay. To further zoom in, this is how each inode block looks like. In total, we have 5 inode blocks, and each and every inode blocks consist of a total number of 16 inode data structures, as shown over here. So the second inode block consists of starting from inode number 16 all the way to inode number 31. Okay? So inode itself typically consists of 128 or 256 bytes, and depending on the file system configuration. Okay, so as a result, a 4 KB disk block typically can consist of multiple, for example, 16 to 32 inode data structures per inode block or per disk block. Okay, and recall that each file or each directory is associated with a unique inode number. So these inodes are essentially the machine understandable, machine readable file names. So that also kind of specify the upper bound limits with regards to how many files together with directories that can be stored by this file system. In this case, since the total number of inode blocks is 5, there are a total number of 5 inode blocks, and each inode block consists of 16. 5 blocks, and each inode block consists of 16 inode structure. So that means for this particular file system layout, it could be used index at most how many unique files, how many different files? It's 80, right? It's 5 times 16 gives you 80. So the maximum number of files or index or directories that could be indexed under the file system is 80 at most. Okay. To further zoom in, this is how each inode data structure looks like. It contains the basic statistic information about the file or the directory associated with it. So the first field is called type. It indicates whether this file related to this inode is a data file or a directory. Okay. So the second and third field, UID and the RWX. So these two fields basically represent the user as well as the permissions associated with it, whether it's read-only, it's read and write, or it's executable, okay? The permissions. And the third and the next two fields, size and blocks, represent the size in terms of number of bytes and the size in terms of the total number of blocks that this file spans, okay? And the next two fields, time and seed time, indicate the access timestamp and the creation timestamp, when exactly this file or this directory gets created. And the second field, links counts, represent how many links or how many directories gets pointed to this particular file. In the last field, address, so it's an array, it's an n element array, represent the addresses of the total number of n data blocks that this particular file spreads, okay? So this is how each and every inode looks like internally as a data structure, statistics to represent, to record the statistics related to a particular file or directory. Okay, so as we've already talked about, each inode is associated with a particular file, so it maintains pointers to the starting address of that particular file or directory, as shown in this case. So these 4 different files has like representative pointers that points to the starting address, starting on this address where the corresponding files get stored on disk, okay? And if that particular inode, if the file spans multiple disks, so let's assume this inode 21. So this inode 21 spans 3 different data blocks, multiple data blocks. So um, it will require 3 entries with the address array, and each element points to one of these on-disk data blocks, each of which is used to store a portion of this file. Okay, so for example, it points to the very first block and a block somewhere in the middle and another block within the last range of this data region. So as an example, okay, just to showcase how a multi-data block inode file looks like. So the next on this data structure is directories. So we're going to just flip through these directory data structures. So because the directories are essentially a file, so just like how a regular file gets stored, we just store a directory exactly the same way. But different file systems may vary. If we're talking about Unix or Linux-like file systems, basically directory entries or the metadata corresponding with directories are exactly the same like the metadata associated with a plain data file. And recall that the very first field of the inode data structure is the type field. And you use that type field to indicate whether this is a regular data file or it's a directory file. Okay? And in practice, a different file system may use different data structures to index the files and directories, to organize directories. For example, you could use a list-like data structure, and more commonly, you could use more efficient tree-based hierarchical data structure, for example, B trees. And in practice, we have B tree-based file system, which uses B trees to keep track of the file-related indexing. So the next set of data structures are the data bitmap and inode bitmap. So this has something to do with the disk space allocation, how to allocate the disk space for storing the file data. Okay, so the question is, how does file system find the free disk blocks or the free inode data structure, free inode blocks? It could use various different data structure, various different ways to keep track of that, right? So one typical way is to use a linked list based free list data structure, which is used to keep track of, to link together all the free blocks that are available for allocation usage. And the second kind of approach is called bitmaps. So let's first take a look at the free list kind of approach. In this case, in this example, it shows how a free list looks like. It's essentially a singly linked list. And this singly linked list has a list hat. So in order to locate some free chunks or free data blocks, you have to traverse through this singly linked list based free list linearly, okay? And in practice, it's not all the free data blocks are not organized and linked together in a sequential or contiguous way, but rather it's jumped randomly from the starting range of the disk and all of a sudden jump to the ending range, the second half of the disk address space and something like that. So it's kind of tricky and pretty inefficient if you want to allocate a large contiguous chunks of multiple data blocks for facilitating sequential disk space allocation. Because a disk is really good at sustaining large sequential IOs, but instead of like small random IOs. And we've talked about this when we discuss the disk properties, right? So seems like free list is not that kind of efficient data structures for facilitating this kind of purpose. Okay. So next, the second type of approach is what is called a bitmap. So as its name suggests, each bit of this bitmap data structure can be used to indicate whether the corresponding data objects or the data blocks is free or in use. And we use the bit value of 0 to represent a free state. And we use a bit value of 1 to represent this data block is under usage, in use. Okay, so it is kind of easy to understand. And each index, it corresponds to a particular data object, data block. For example, the very first bit, a bit 0 corresponds to data block number 0. And the last bit, a bit n-1 corresponds to the last data object on disk. Okay, assuming the whole data region consists of a total number of n data blocks. Okay, in this case. Okay, so the trade-off is, just as I've mentioned, free list is kind of tricky and sometimes not efficient if you try to get contiguous space for taking advantage of the good sequential I/O performance that you can easily get from a mechanical hard disk drive if we're talking about HDDs. Okay. Whereas the second approach, which is a bitmap, this is easy because you can just try to perform this bitwise operation in order to easily allocate contiguous space for, say, large files. Okay, so this is a typical trade-off that we're looking at to compare free list against the bitmap data structures. Okay, so a Unix-like operating file system, it uses the bitmaps to keep track of the data region space allocation as well as the inode region resource allocation. So the third metadata block is reserved for storing the data bitmap. And the second metadata block, and here we're talking about metadata block. Okay, so the second one is reserved for storing the inode bitmap, starting with a letter small I. Okay, so how does it look like? So next we're going to take a look at this, the last data on this data structure, which is called super block. Okay, this super block is the ultimate kind of metadata that is used to keep track of this global file system configuration with regards to, the block size that this file system uses, how many inodes are there, and how much free space does this file system image still have, and something like that. So all this global metadata global metadata is stored and kept track of within a particular on this data structure, which is called super block. Okay, and the super block, the very first metadata block of this file system image, is reserved for storing this super block. Okay, so to zoom in, this is how exactly the reserved metadata fields look like. Okay, the very first 4 KB, the data metadata block or the disk sector is reserved for the super block. It indicates, it's used to keep track of the global file system configuration with regards to the file system size, how much free space does it still have, the granularity of the data chunks, and so on and so forth. And then it comes with another 4 KB, which is the inode bitmap, which is used to indicate which inode. Okay, so this inode table, which inode within this inode table is free and which inode has already been allocated. Okay, and next move on to this data region bitmap, and this is used to keep track within this data region which particular data block is in use and which particular data block is otherwise already used. Okay, so this is corresponding with all of these, the rest of the range. Okay, the data range, the data region. Okay.